You've seen number patterns before, right? Some are super simple, some are tricky, but a special few hide a secret, a kind of hidden engine that can generate infinite complexity from incredibly simple rules. And today, we're going to go find it.
Okay, so let's just dive right in. On the left, you've got a sequence you could probably solve in like a second. You just add 2 every time. Easy. But on the right, 0, 1, 1, 0? I mean, it looks kind of random, doesn't it? Is there even a rule here? What could possibly be generating this pattern? Well, that's the mystery we're going to unravel today.
All right, our search begins. How do we even start to find a pattern like this? Well, our first instinct is almost always to look for some kind of math formula. First, let's just get our terms straight so we're all on the same page. A sequence is really just a list of numbers in a specific order, and each number in that list is called a term. So for our mystery sequence, the first term is 0, the second is 1, the third is also 1, and so on. Pretty simple, right?
See, usually when we're hunting for a pattern, we're really looking for a formula, a rule where the value of any term depends on its position in the line, which we just call n. For example, the formula n squared gives you that sequence of perfect squares, 1, 4, 9, 16. If you want the 10th term, you just do 10 squared. Done.
Which, of course, brings us back to our puzzle. What kind of formula based on n could create this? It's not adding, it's not multiplying, it's not squaring. The rule isn't obvious at all. And that's because we've been looking in completely the wrong place.
The answer isn't a formula that you can just write down on paper. It's a machine you can actually build. So let's pull back the curtain and take a look at the secret engine that's powering this whole thing. This is the big aha moment. The rule isn't an equation, it's a machine. A very, very simple machine called a finite automaton. And this little diagram right here, with just 2 states, Q0 and Q1, and a couple of arrows, that contains the entire instruction manual for generating that infinite sequence.
And this brings us to the key idea for today. A sequence like this is called an automatic sequence. And what makes it special is how you find the nth term. You take the number n, you break it down into its digits, and then you feed those digits into one of these little machines. The state the machine ends up in, that's your answer. So I know what you're probably thinking. How in the world does that tiny diagram generate such a weird, complicated pattern? Let's break it down step by step. It's actually pretty cool.
Here's the 4-step recipe. First, you pick which term you want to find. Let's say the 3rd term, so n is 3. Second, you convert that number n into its binary, or base 2 digits. For 3, that's just 1, 1. Third, you feed those digits, one at a time, into our machine, always starting at the start position. And fourth, wherever the machine lands after the last digit, that state's output is your answer.
Okay, let's watch this machine do its thing. Let's find the 3rd term, so n equals 3. In binary, that's 11. We start at Q0. The first one tells us to follow the arrow to Q1. The second one tells us to follow the arrow back to Q0. We end it in state Q0, and its output is 0. And look at that! It matches our sequence perfectly. Let's try n equals 4. Binary is 1, 0, 0. We start at Q0. The 1 moves us to Q1. The first 0 keeps us at Q1. The second 0 keeps us at Q1 again. We end at Q1, and the output is a 1. It works every single time. So this one little machine perfectly generates our mystery sequence. But this isn't just a one-off party trick. This simple machine method actually unlocks an entire universe of other incredible patterns. The sequence we've been looking at this whole time is actually famous. It's called the Thue Morse sequence. But by designing just slightly different machines, you can generate all sorts of other amazing patterns. From the Rudin Shapiro sequence to the pattern you get from repeatedly folding a piece of paper, each one is powered by its own unique but still very simple little engine. So, okay, this is a very cool mathematical idea, for sure. But what's the bigger picture here? Why is this so important? Well, this concept actually reveals some really deep truths about numbers themselves. Take Cobham's theorem, for example. It's a profound idea. It basically says that these automatic sequences are kind of locked to a specific number base, like the binary we've been using. The only way a sequence can be generated by a machine in 2 different bases, like say base 2 and base 3, is if that sequence is incredibly simple. just a pattern that repeats over and over again. It proves this deep, fundamental link between the machines that compute and the very nature of numbers. And this really is the biggest takeaway. Automatic sequences create this stunning, beautiful bridge between two massive fields: number theory, which is the pure study of numbers and their properties, and theoretical computer science, the study of what machines can and can't do. They show us that these two worlds are, in a way, speaking the same language. At its heart, this is just a mind-blowing idea. It proves that patterns of infinite length and mesmerizing complexity can pop out of a tiny, finite set of simple rules, a little machine that you could literally draw on a napkin. It really makes you wonder, doesn't it? If a machine you can draw on a napkin can generate this kind of infinite complexity, what other profound secrets about our universe are hiding in the language of simple machines, just waiting for us to find them?